This is the scale of modern hydroelectric infrastructure. Millions of tons of concrete holding back entire lakes, functioning as massive stores of potential energy. Expanding our clean energy capacity usually implies a need for more of these colossal structures. This footage shows the raw power of a dam spillway, but the real opportunity for growth is often invisible. A 5% increase in efficiency at existing sites translates to gigawatts of additional power added to the national grid. That 5% growth occurs within the fluid dynamics of how the machine actually harvests the water's energy. The early designs relied on impulse turbines. These operate by shooting a high-speed jet of water through a nozzle to strike buckets attached to the outer edge of a wheel. This method leaves significant energy unharvested. Because the water remains at atmospheric pressure when it strikes the buckets, the system only captures kinetic energy, leaving the intense pressure of the reservoir behind it untouched. To capture that missed potential, the engineers began sealing the wheel inside a casing and submerging it entirely. Shifting from a simple kinetic strike to a state of total fluid immersion resulted in the reaction turbine. This schematic shows the defining requirement of a reaction turbine. The runner must be completely submerged and kept full of water at all times, with no access to free air. Water enters tangentially at high pressure. As it moves along the spiral casing, stay vanes turn the flow inward toward the central runner. As the water glides over the rotating blades, it transfers momentum using both kinetic and pressure energy. The machine creates a massive pressure drop across the runner to extract the maximum possible energy from the fluid. Efficiency depends on matching the turbine design to the environment's flow rate and head, the vertical distance the water falls. In the 1840s, James B. Francis developed a design for medium head environments, typically between 100 and 450 meters. This is a mixed-flow turbine. As these arrows show, water enters the runner radially from the perimeter and is forced to exit axially down the center. The runner is densely packed, typically using 16 to 24 fixed vanes to handle these medium-pressure environments. The Francis turbine essentially functions like a centrifugal pump running in reverse, making it a standard choice for most major dams. Different challenges arise in low-head geographies, where water drops only about 50 meters, but features massive, fast-moving flow rates. Victor Kaplan solved this by developing a propeller-based turbine designed for lower pressures and higher volumes. This photograph shows the axial flow structure of the Kaplan. It uses far fewer blades than a Francis, usually only 4 to 8 vanes mounted on a central hub. The Kaplan maintains efficiency through double regulation. This allows the machine to physically adjust its components to optimize the flow. Unlike fixed Francis blades, the Kaplan runner has an adjustable pitch. The blades rotate on their own axes, changing their angle against the incoming water to handle variable flow. This adaptability allows the Kaplan to reach high specific speeds, where rigid turbines would lose efficiency. These industrial powerhouses demonstrate the scale at which these specialized machines operate side by side. Choosing between a Francis turbine for a steep dam or a Kaplan for a fast river is a deliberate engineering decision to capture every available drop of energy. These rotors are refined for precise geometry to chase incremental gains in efficiency. In the search for clean power, that 5% growth is earned by engineering a mathematically perfect reaction to the environments we already inhabit.